In this video, I'm going to walk through the complete design process presented in this 2025 research paper, from the first LT-SPICE simulation all the way to the validation of a complete EMG wristband. Every quote you will see throughout this video comes directly from this paper, which I've linked in the description below. Even if you don't plan to build the exact same hardware, I think understanding this engineering process is incredibly valuable. So, with that said, let's get started. Before we start, if you're new here, this series is all about trying to recreate Meta's EMG wristband from scratch. We are going to explore the hardware, electronics, machine learning and everything in between. So if you want to follow the entire journey, make sure to check out the playlist. From a functional perspective, an EMG wristband can be divided into three main blocks. The first one is the sEMG acquisition unit. This is where the actual muscle signals are collected, amplified, and filtered before being converted into digital data. The second block is the control unit, which reads those analog signals using an analog to digital converter and manages the acquisition process. For this video, we're going to focus on the first block. At the very end, we will briefly come back to the control unit to see how everything is integrated into the final wristband. One of the first design decisions when building an EMG system is choosing how the electrodes acquire the signal. There are several possible acquisition modes. For example, we got monopolar, bipolar, also called single differential, and finally double differential. Each configuration has different advantages and disadvantages regarding noise rejection and spatial selectivity. In this video, we're going to focus on the single differential configuration, since it's probably the most common solution. Throughout the paper, this configuration is referred to as SD3EL, which stands for single differential with 3 electrodes. The two outer electrodes measure the muscle activity, while the center electrode acts as the reference. If you have seen the previous episode, you will probably notice that this looks very similar to the control kit configuration. Before building any hardware, the first thing the authors do is simulate the entire analog front end using LT-SPICE. One important thing to remember is that this isn't just one circuit. Every EMG channel inside the wristband contains one of these analog front ends. So if your wristband has 8 channels, you're essentially repeating this circuit 8 times. Instead of looking at the schematic all at once, let's go through it block by block. The first block is the muscle signal itself. Obviously, we can perfectly simulate a real muscle contraction. Instead, the authors generate a signal that statistically behaves like a real sEMG signal. The paper describes it as follows. For the simulation of the design circuits, a muscle signal was generated as a Gaussian white noise bandpass filtered between 10 and 350 Hz. So instead of trying to model an actual muscle, they generate a Gaussian white noise and then filter it so that its frequency content resembles a physiological EMG signal. Throughout the paper, you will also see the term RMS, that simply stands for root mean square. We will use this value later to calculate the gain of the circuit. Now, before the signal reaches our circuit, it has to travel through the electrode skin interface. This interface introduces an impedance that has a huge impact on the signal quality. The paper explains, before the signal reaches the input of the EMG sensory circuit, it passes the simulated electrode skin interface, which introduces an impedance. The electrode skin impedance ranges between 10 to the power of 3 ohm and 10 to the power of 7 ohm. One of the biggest problems is that this impedance is never exactly the same for every electrode. That imbalance converts part of the common mode interference into differential noise, making EMG acquisition much more difficult. To reproduce this effect, the authors model each electrode using an equivalent electrical circuit. The paper continues. The difference in skin electrode impedance causes amplification of the common mode voltage through the voltage divider effect. By including this model, the simulation becomes much more closer to what happens in a real EMG measurement. At this point, the signal finally reaches the analog front end. The problem is that we are dealing with voltages of only a few millivolts. That's far too small for an analog to digital converter. So, the first active stage of the circuit is the instrumentation amplifier. The paper describes it as follows. The sEMG sensor circuits start with an amplification stage, in which the voltages of two inputs from two electrodes are subtracted and multiplied by a factor. In other words, the instrumentation amplifier subtracts the signals coming from the two electrodes, removing as much common mode interference as possible while amplifying only the muscle activity. Once the signal has been amplified, we are still not ready to digitize it. First, we need to remove unwanted frequencies. The paper explains. The amplified signal is bandpass filtered using a second-order active A-pass Sallen-Key filter followed by a second-order active low-pass Sallen-Key filter and then shifted to half the supply voltage to accommodate the analog-to-digital converter, which accepts only positive input voltages. So the signal first passes through a bandpass filter that keeps only the useful EMG frequencies. Then, before entering the analog-to-digital converter, DC offset is added so that the entire waveform is shifted above 0 volts. Without the bias stage, the negative half of the EMG signal would simply be clipped. Now that we have looked at every block individually, let's see how the simulation is actually performed. The authors didn't simply connect everything together and look at the output. Instead, they define a complete testing procedure. The paper states, in order to test the circuit functionality, inputs of the simulation include noise introduced by the skin electrode interference, power line interference voltage, and the sEMG signal. The input to muscle signal is delayed by 0.0025 seconds between the electrodes to account for the propagation time. Let's break this down. The simulation has three different inputs. First, we have the muscle signal. Notice that the signal arrives at each electrode with a small delay. Then we have the common mode interference, which represents the power line noise affecting every electrode. Finally, a random noise is added to simulate a more realistic acquisition environment. Now that we understand the simulation inputs, we can finally look at the parameters used to evaluate whether the analog front-end is actually working correctly. Now that we understand how the simulation is performed, let's look at what the authors actually measure. The paper evaluates 4 different parameters. Each one tells us something different about the performance of the analog front-end. The first is the differential gain. The second is the common mode gain. Using these two values, the common mode rejection ratio can be calculated. Finally, the signal-to-noise ratio, or SNR, is evaluated. Let's go through them one by one. The first parameter is the differential gain. To measure it, the simulation is performed using only the muscle signal. No common mode interference and no random noise are included. Once the simulation is complete, the RMS value of the input signal and the RMS value of the output signal are measured. The gain is then calculated as RMS out divided by RMS in. The paper explains. The total gain in the simulation was calculated by comparing the RMS value of the EMG signal input and the RMS of the output signal when only the muscle signal is used as input and not the power line interference or noise. Basically, this tells us how much the EMG signal is being amplified by the circuit. Next, the authors evaluate how much the common mode interference passes through the circuit. This time, the simulation is repeated using only the common mode voltage, which in the paper represents the power line interference. The muscle signal and the random noise are removed. Again, the input and output RMS values are measured and the gain is calculated as RMS out divided by RMS in. The paper states, the gain of the common mode voltage was calculated analog. Power line interference is introduced into the circuit but no muscle signal and the RMS values of the output is divided by the RMS value of the input. Ideally, this value should be as close to 0 as possible. The lower this gain is, the better the circuit rejects external interference. Now that we know both gains, we can calculate one of the most important parameters, the common mode rejection ratio. This parameter tells us how well the circuit amplifies the useful muscle signal while rejecting common mode noise. It is calculated using the differential gain and the common mode gain. The paper reports the following equation. The paper explains: common mode rejection ratio was calculated for every circuit, once with an equal electrode skin impedance and once with a 10% imbalance. One interesting detail is that the authors don't calculate the common mode rejection ratio only once. They repeat their entire simulation under two different conditions. The first assumes that every electrode has exactly the same skin impedance. The second introduces a 10% impedance mismatch between the electrodes. This is much closer to what happens in real measurements, where no two electrodes behave exactly the same. The final parameter is signal-to-noise ratio, or SNR. Unlike the previous measurements, this time the simulation includes all three inputs at the same time: the muscle signal, the common mode interference, and the random noise. The idea is simple. Instead of looking only at how much the signal is amplified, we now evaluate how clearly the useful signal stands out from the noise. The paper explains. In the simulation, the common mode component is known, allowing direct calculation of the common mode rejection ratio. In a real-world measurement, this is not feasible. Therefore, the SNR is used as the primary criterion to evaluate circuit performance in practical measurements, but not in the simulation. In other words, during the simulation, the common mode rejection ratio is the preferred metric, because we know exactly how much common mode interference was applied. Once we move to real hardware, however, we no longer know the exact amount of interference entering the system. For that reason, the SNR becomes the primary performance metric during experimental validation. Now that we have seen all the parameters during the simulation, the question is, how do we know if the circuit is actually good? The paper answers this by defining two primary validation criteria. It states, the two primary criteria tested in the simulation are the common mode rejection ratio and the amplification factor, the gain. So before building any hardware, the authors verify that the simulated circuit provides enough gain to properly amplify the EMG signal and a sufficiently high common mode rejection ratio to reject common mode interference. Finally, these simulated values are compared with values reported in previous scientific literature. As the paper states, validation parameters were validated by comparing the simulated results with values reported in the literature. If the simulated gain and the simulated common mode rejection ratio are consistent with previously published work, the analog front-end can be considered successfully validated. At this point, we are finally ready to move from simulation to actual hardware and start designing the PCB. At this point, we have successfully validated the circuit in the simulation. The next step is to turn that design into real hardware. This means designing both the PCB and the electrodes, since together they form the complete analog front-end. One design choice that immediately caught my attention is how the authors physically separated these two parts. Instead of placing everything on a single PCB, they designed the electrodes and the circuitry as two stacked boards. The paper explains why. The sensor circuitry and the electrodes are designed in stacking configuration to enable connecting different electrodes to the same circuit. This is a very clever design choice. By separating the circuitry from the electrodes, they can independently test different electrode designs without redesigning the analog electronics every time. Likewise, they can improve the circuitry while keeping exactly the same electrode module. This makes the whole development much easier. Let's first take a look at the electrodes. The paper describes the single differential module as follows. The first, designated as 3-electrode, is used with a single differential 3-electrode configuration and features 3 electrodes with a 10 mm inter-electrode distance. The electrodes themselves are also described in detail. The paper states, the electrodes have a rectangular contact area with a size of 5 times 6 mm and are made from stainless steel. Finally, the electrodes are attached to the PCB using conductive silver epoxy. The electrode material is a medical degree stainless steel, chosen for its biocompatibility, corrosion resistance, and affordability. Electrodes are fixed on the PCB using a conductive silver epoxy glue from EMG Chemicals. After gluing the electrodes, the authors also verified that every electrical connection had a low resistance. The paper explains. Each electrical connection between an electrode and its corresponding PCB pin was tested. Connections with a resistance below 1 kΩ were considered acceptable, as this is negligible compared to the much higher skin electrode impedance variance. So even something simple as attaching the electrodes is treated as part of the engineering process. Now let's look at the analog circuitry itself. The first major component is the instrumentation amplifier. The paper explains. The ED8224 was selected due to its high input impedance, compact footprint, and compatible operating voltage. This is the same amplifier responsible for the differential amplification stage we discussed earlier during the simulations. For the filter stage, however, the authors selected a different integrated circuit. They write, the ED8244 operation amplifier is employed in the filter and bias stage, which requires 3 op-amps. The ED244 quad op-amp provides 4 high-performance op-amps within a compact package and is recommended for silent key filter application. Since the filter requires multiple operational amplifiers, using a quad op-amp allows the entire design to remain compact. One interesting aspect of the design is the power supply. At first glance, you might think that a simple 3.3 volt supply would be enough. However, the paper explains that this is not the case. A voltage converter, although not directly affecting the signal, is essential for amplifying the sEMG signals. The sEMG signal can be partly or fully negative, requiring instrumentation amplifiers to handle negative input voltages. To accommodate this, the amplifiers need a negative supply voltage rather than only a ground reference. The voltage converter, TPS, meets this requirement by converting 3.3 volt to negative 3.3 volt, providing the necessary negative supply voltage for the instrumentation amplifiers. So even though the digital analog converter eventually measures a positive biased signal, the analog circuitry itself still needs a negative supply voltage to correctly amplify signals that naturally swing below ground. At this point, the analog front-end has been completely designed. We now have the electrode module, the analog circuitry, and the complete PCB implementation. The obvious next question is, how do we know if all of this actually works in real life? This is where the validation phase begins. Before looking at the individual tests, however, there's one important thing worth mentioning. Throughout the rest of the paper, the authors compare their hardware against the 400, which is considered a gold standard EMG acquisition system for research applications. The 400 is an extremely expensive piece of equipment, costing several thousands of euros, which makes it inaccessible for most hobbyists and even for many research labs. However, I think that the overall validation methodology is still extremely valuable. Even if you don't have access to the exact same equipment, the process of validating the hardware remains essentially the same. So, with that in mind, let's see how the authors validated first the circuitry, then the electrodes, and finally the complete EMG sensor module. The first thing the authors validate is the circuitry itself. Notice that at this stage we're not using human EMG signals yet. Instead, they inject a known electrical signal into the circuit, so that every measurement can be repeated under exactly the same conditions. This removes all the variability introduced by muscles, skin, electrode placement, and even different subjects. The paper explains how the measurements were performed. To evaluate gains and SNR independently of human variability, a validation trial was performed using a generated voltage source. The digital oscilloscope served as a signal generator to produce a sinusoidal waveform with a constant amplitude and frequency. The analog output was measured using a red lab at a sampling rate of 2000 samples per second. Data post-processing was performed in MATLAB 2024. So the setup is actually quite straightforward. A signal generator produces a clean sinusoidal signal. The analog front-end processes that signal. Finally, the output is acquired using an external data acquisition and analyzed in MATLAB. Once the measurements have been acquired, the question is, what do we compare them against? This is where the 400 comes into play. The paper explains. For comparison with an established sEMG system, the 400 with an AD16 adapter was used in combination with the OT BioLab 24 software. However, one important limitation immediately appears. The paper continues. According to the user manual, the 400 system provides a fixed analog gain, thus making a direct gain comparison not feasible. Consequently, gain measurements were performed limited to the design circuit to verify if the target gain is achieved. This is actually a very important point. The gain cannot be directly compared with the 400 because the commercial system performs its own internal amplification and scaling. Instead, the gain is simply compared against the expected value obtained during the simulations. The SNR, on the other hand, can be compared with the 400, making it the main parameter used to evaluate the quality of the circuit. To verify that the circuit behaves correctly under different operating conditions, the authors repeated the measurements using several different input signals. The paper states, 3 different frequencies were tested, in combination with 3 different amplitudes, to assess if the gain is dependent on the frequency. So in total they performed 9 different measurements, covering every possible combination of frequency and amplitude. Another interesting detail is how the signal was injected into the circuit. Instead of reproducing the delayed differential signal used during the simulations, the authors simplified the setup. The paper explains. The waveform is only applied to one input, while the other input is referenced to ground, not the delayed signal as in the simulations. This makes the experimental setup much easier while still allowing the performance of the analog front-end to be evaluated. Once all 9 measurements have been acquired, the authors analyze both the signal amplitude and its frequency spectrum. The paper states, for each introduced frequency and amplitude, both RMS and FFT analyses were performed. So for every one of the 9 measurements, they calculate the RMS value, the FFT of the signal, and the signal-to-noise ratio. The FFT is particularly useful because it allows them to directly compare the useful signal with the unwanted 50 Hz power line interference. By repeating this analysis across multiple amplitudes and frequencies, they can verify that the analog front-end behaves consistently under different operating conditions. Once the circuitry have been validated using a generated signal, the next step is to test it with an actual human muscle. For these measurements, the authors switched from a signal generator to real sEMG recordings. The paper explains. A secondary comparison between the design circuits and the 400 reference system was performed in a single subject study to assess the analog acquisition of sEMG signals. At this point, the validation procedure changes slightly. Instead of using a generated sinusoid, the signal now comes directly from muscle contractions. The paper explains how the SNR is calculated. Measurements were carried out following the protocol outlined in section 4.2. The SNR was calculated using the formula. The noise is described as the full RMS of the rest measurement. The signal represents the part of the total signal that is different to noise. This one right here. The total signal is the output signal measured by the data acquisition hardware. In all tests conducted according to the protocol, noise was defined as the RMS value of the 5-second rest period measurement. The SNR served as the primary metric for evaluating performance in the single subject circuit validation. In practice, the procedure is very simple. First, they record the subject while the muscle is completely relaxed. That recording is considered the system noise. Then they record the muscle contractions. Those recordings contain both the EMG signal and the noise. By subtracting the noise contribution, they estimate the effective muscle signal and calculate the SNR. But to make these measurements meaningful, every subject has to follow exactly the same protocol. And that's exactly what the authors designed next. Since the muscle activity changes from person to person, the authors designed a standardized protocol so that every measurement could be compared fairly. The paper explains, a testing protocol was developed for testing different electrodes and sensor configurations. This protocol was consistently applied across all human subject trials to establish a comparable dataset. So every measurement is performed on the biceps. This minimizes interference from closer muscles and makes it much easier to place every sensor over the same muscle. The paper then describes how each subject performs the measurement. To ensure consistent muscle contractions, the subject positioned the upper arm on an angled profile, while the lower arm was held horizontally, resulting in an elbow flexion angle of approximately 30 degrees. The protocol comprises 6 trials with sequentially added weights to the hand. So the protocol is actually very systematic. The first recording is simply the subject relaxing the muscle. This becomes the reference measurement used to estimate the system noise. Then, the subject performs 6 isometric contractions, while holding weights from 1 kg to 6 kg. Each contraction lasts 7 seconds, but only the middle 5 seconds are analyzed. This removes both the lifting movement at the beginning and the release at the end. Because every subject performs exactly the same test, the resulting data becomes much more reliable. So far we have validated the circuitry. The next step is to validate the electrodes themselves. To do this, the authors compare their custom electrode module against the commercial hydrogel electrodes connected to the 400. The paper explains, besides the SNR, the impact on the frequency spectrum served as a secondary criterion for the evaluation of the results. Besides looking at the signal-to-noise ratio, they also analyze the frequency content of the EMG signal. Using the FFT, they calculate the power density spectrum, or PDS, and from that they determine the mean frequency of the signal. This allows them to evaluate whether the custom electrodes affect the frequency content compared to the commercial reference electrodes. One final detail mentioned by the paper is that all recordings are post-processed using a digital notch filter. It states, for evaluation of the frequency spectrum, a digital notch filter at 50 Hz was applied during post-processing to reduce power line interference. This removes the final power line interference before analyzing the frequency spectrum. At this point, both the circuitry and the electrodes have been validated individually. The obvious next step is to combine them together. This is what the paper refers to as the sEMG sensor module. Instead of validating the two components separately, the complete module is now evaluated as a single system. The paper explains, the validation process involved comparing the sEMG sensor module with hydrogel electrodes connected to the 400, as in the validation of the circuitry. The acquisition hardware used during these measurements is the same external data acquisition introduced earlier, the Red Lab from Mailhouse Electronic. Since both the circuitry and the electrodes have already been validated, this final step focuses on the performance of the complete acquisition chain. The paper summarizes the evaluated parameters as follows. Parameters analyzed included power density spectrum, raw sEMG signals, and mean frequency, with special focus on the transfer functions effect among the design circuits. In other words, the authors now verify that the complete sensor module behaves as expected when every component works together. At this point, the entire analog frontend has been validated. The only thing left is integrating these modules into the wristband itself and designing the electronics responsible for digitizing and transmitting the acquired data. Up until now, we have only looked at one EMG acquisition module. But the real wristband obviously contains more than one channel. So how are all these modules connected together? This is where the control unit comes in. The paper introduces the complete wristband architecture, where each EMG module contains not only the analog front-end we have been discussing, but also the electronics required to digitize the signal. As you can see, each module is much more than just an instrumentation amplifier and a few filters. In addition to the analog circuitry, every module also includes an analog to digital converter and a microcontroller. The analog to digital converter converts the analog EMG signal into digital data, while the local microcontroller manages the acquisition and communicates with the rest of the wristband. Instead of connecting every analog signal directly to a central processor, each module performs its own acquisition locally. The data is then transmitted over SPI to a master controller. Finally, the master sends all the collected information through Bluetooth to a computer. The paper describes this process as follows. The wristband module contains a stack of PCBs for the electrode, analog circuit, and data acquisition inside a housing that matches the length and width of existing modules. The 12-bit sEMG data from the ADC is converted to a 8-bit data to send via SPI to the master module. The master module transmits the data to a laptop via Bluetooth. The data is stored with MATLAB using a virtual communication port. So overall, the data flow is actually very simple. The muscle activity is acquired by the analog front-end. The analog digital converter digitizes the signal, the local microcontroller forwards the data through SPI, then the master controllers collects everything and finally send the data over Bluetooth to the computer. Once the complete wristband was assembled, the final step was to test it with real users. The paper explains, 2 wristband modules, single differential and double differential, were tested. The user study involved 6 subjects who each wore the wristband secured to their comfort. Each subject followed the test protocol for both configurations. Notice that they reuse exactly the same testing protocol introduced earlier. This means that the only variable changing throughout the experiment is the hardware itself, making the comparison much more meaningful. The paper also states, the user study data was anonymized and randomized to protect participant privacy. Finally, the recorded signals were analyzed using the same metrics introduced during the previous validation stages. The paper explains, the user study measurements demonstrated a significant reduction in susceptibility to power line interference, making the use of a notch filter unnecessary. The study analyzed parameters such as SNR and mean frequency across sensor configurations and subjects. At this point, the complete validation process is finished. The authors have validated the simulation, the analog circuitry, the electrodes, the complete sensor module, and finally the entire wristband with human subjects. Personally, I don't think I'm going to replicate this EMG module. From everything I've studied so far, the metaneural band seems to use a different architecture and different design choices than the ones presented in this paper. However, I still think this paper will become one of my main references throughout this series. Whenever I design, test or validate my own hardware, I'll probably come back here to compare my results and make sure I'm following a solid engineering process. So even if we never build this exact wristband, I hope this video has been useful in showing not only what the authors built, but also how they proved it actually works. Before ending the video, I would like to give a quick shout out to someone who has been working on a very similar project. His name is Takuo, he's from Japan and is actually the same age as me. Over the past weeks we have been exchanging ideas and technical information about EMG hardware, and he's built an impressive project that recreates many of the concepts behind the original control kit. He's currently improving his design, and I honestly think his work deserves a lot more attention. If you're interested in EMG hardware or wearable electronics, go check his X account and consider supporting his work. Thanks for watching, this was quite a long video and I'm going to see you in the next one.